What is going on, Skyhawks? Hello and welcome. Today we're going to be talking about simplifying exponents of exponents. Right? Exhibit rolls up in here and he says, "Yo dog, I heard you like exponents, so I got you some exponents for your exponents." Right? That's what we're talking about here. We're talking about exponents on exponents. It's crazy. It's meta. It's self-aware. So let's go ahead and dig into this and see what it's all about. So remember, we want to ground ourselves, right? Ground ourselves in the fundamentals and watch how they take us to the places we need to go. Exponents represent repeated multiplication. Repeated. That wasn't a mistake. That was intentional. Thus, the exponent of any term, even of an exponent, can be represented as repeated multiplication. Right? Let's go ahead and think about that. We're not going to overcomplicate this. If something has an exponent, we can repeatedly multiply it. That's what it means. So, even if something has double exponents, that's okay. We can still go ahead and expand it the same way we would anything else with an exponent. Right? Our concept didn't change at all. It's just repeated multiplication. Okay? So we can expand this multiplication and thus simplify it further. Okay? So right, it's still just repeated multiplication. And we're going to explore with this. We're going to explore doing this with our fundamentals. And we're going to see a pattern emerge from this. Now, spoiler alert, here's the pattern. If you don't want to hear the pattern, you want to discover it for yourself, go ahead and skip to example number 1. But if you want to just go ahead and hear it, make your life maybe a little bit easier and just learn the pattern and roll with it, here it is. Likewise, since exponents represent repeated multiplication, right? Remember, repeated multiplication, that's what exponents are. And exponents are found via counting, aka adding, right? If I have 3 things, 1, 2, 3, I counted up to 3. I just added up those 3 things, added 3 single things, multiple multiplied terms. Okay, so let's go ahead, let's digest that because it's a big idea. Exponents are repeated multiplication, and exponents are found via adding multiplied terms. Okay, so exponents are just adding those multiplied terms. So the exponents of exponents can be thought of repeated addition of multiplied terms. Okay, now let's go ahead and, so key word in there, repeated addition. What is repeated addition? It's multiplication, right? 2 times 2 is the same as 2 plus 2. 3 times 2 is the same as 2 plus 2 plus 2. Multiplication is just repeated addition, aka multiplied exponential terms. Right? So when we have exponents, it's repeated multiplication. So when we have an exponent of an exponent, because remember, the exponent is just counting or adding the number of things multiplied, right? We are repeating the number of times we added. Repeating the addition is multiplication, right? Very big logical steps there. I know that's a lot of logic to digest. But that's what's going on, and that's why we're going to see this really beautiful shortcut come out. Okay, so expressed in math symbols, it's written like this. Quantity, right, quantity means we have parentheses around it, m to the power of a times n to the power of b, all raised to the power of c, equals m to the power of a times c, so our exponent is a times c, n to the power of b times c, right? So our exponent is b times c. Look at what happened there. We distributed to the exponent. We had an exponent of an exponent and we distributed it. Because the exponent of an exponent is repeating that addition. Repeated addition is multiplication. Crazy, right? Super crazy. So let's go ahead and do this process, right? Example number 1. Taking our exponent and putting it to each one. Now, like I said, we're first going to do this the old-fashioned way, right? Exponents just mean repeated multiplication. So let's go ahead and just make it repeated multiplication. Now, let's not overthink this. I have this term to the power of 3. I have this stuff multiplied 3 times. Okay? So let's go ahead and write all that stuff out multiplied 3 times. Right? That's my first one. 3 times x to the power of 3 times y to the power of 2 times 3 times x to the power of 3 times y to the power of 2. That's my second one, right? Second one of that thing that's being multiplied 3 times. And my third one, 3 times x to the power of 3 times y to the power of 2. Okay? That's all it is. We expand it just like that, and now we got rid of the exponent to the exponent, and we can now take it from here and go ahead and simplify it just as we would any other way. Okay, so first let's go ahead and bring those coefficients out. Coefficient, the thing that multiplies the variable, right? So we have a 3, and a 3. So 3 times 3 is 9, and 3 times another 3 is 27. Okay, now for these exponents, and that's x to the power of 3. My bad for the bad handwriting. Okay? Right? We have 3x's being multiplied here, another 3x's being multiplied, and another 3x's being multiplied. So how many x's in total do we have being multiplied? Well, we have 3, and we have another 3. So we're going to have 9x's being multiplied. 9, or x to the power of 9. What about y? Right? We have y to the power of 2. So we have 2 y's being multiplied, 2 y's being multiplied, and another 2 y's being multiplied. Right? So 2, another 2, and another 2. That's going to be 6. Y to the power of 6. And just like that, it's simplified. Now, right, let's go back and let's use this rule. Let's use this pattern. Right? This pattern of recognizing, hey, my repeated addition that I did here, just adding up 3, 3, and 3 is the same as multiplying 3 times 3, right? We had 3 3's there, and we had 3 2's there, so we can just multiply that. So 3 times 3 is 9. 3 times 2 is 6. Okay? Right? That shortcut, actually, you know better, it's a smart cut. That's really what it is, right? It's a smart cut. It's a very logical and very well thought out smart cut. That smart cut saves us a bunch of time. But realize if you depend just on the smart cut without seeing the fundamentals underneath it, you don't understand it. Maybe you get this problem right, but a more difficult one comes along, it knocks your socks off. Right? You go to the next grade level, and now you need to use this thing more explicitly, more in depth. And you're going to get your world rocked again, because you don't have those fundamentals. Okay? Let's go on to the next example. So, just to really drive home the fundamentals of this, we're going to do it this way, like we did. We're going to just look at this and say, okay, I just know an exponent's repeated multiplication, and I'm just going to run with that. Right? So all that stuff inside that parentheses, doesn't matter what it is, I just know I'm multiplying it 3 times. So here's the first instance of everything inside the parentheses being multiplied 3 times. Okay, that's the first instance of it. Times the second instance of it. 3 times x to the power of 2 times y to the power of 3 divided by 3 times x to the power of 1, right? Just all that stuff. That's the second grouping of it. And then the last, right? This last grouping of it to bring us to our third multiplication of it. Alright? Now let's go ahead and simplify this. We're going to bring our coefficients to the front. I have 3, 3, and 3. 3 times 3 times 3 is 27. And on the bottom, same thing. 3 times 3 times 3 is 27. Okay. Now, let's go ahead and see, let's count our x's, right? We have 2 x's being multiplied here. We have 2 x's being multiplied here and another 2 being multiplied, right? That's going to be a total of 6 x's being multiplied. Alright, now let's go ahead and look at the bottom. This may look a little weird, but that's okay, right? Because we have negative 1 of our x's, we have another negative 1 of our x's, and another negative 1 of our x's being multiplied. Okay, so this is a deficit. This is a backwards counting, right? A loss. You know, we have a negative of x that's not being multiplied, or that's being taken away from the multiplication, right? Another one that's being taken away from the repeated multiplication, another one being taken away. Imagine you lose 3 times, and each time you lose 1. You lose a total of 3. So that's going to be x to the power of negative 3. Okay? And then finally our y's. We have 3 y's right here, 3 y's right there, and 3 y's right there. So y is going to be multiplied a total of 9 times. Alright? And now let's go ahead and take care of that negative. Side note, you could have taken care of the negative right there. And that actually may have been a little bit smarter. But I just went ahead and condensed this. Okay? You could have taken care of it right there. It's going to get you to the same answer. So, realizing, just quick aside, we are going to learn a few rules for this. We're going to learn a handful of rules, and as long as you follow those rules, as long as you don't break any of the rules, you can apply them in any combination to get the same answer. Right? So the ways to do this are endless. You can do it any way you like, in the way you like most. Okay? Always remember that. Alright. Now, I'm going to go to the side. We're running out a little bit of paper. Poor planning. Shame on Mr. Z. And we're going to calculate this over here. So, that x to the power of negative 3, or x negative repeatedly multiplied by 3, right? Or negative repeated division of 3, we bring that to the top. Okay? So we'll bring that x to the negative 3 to the top, so it's x to the power of 3. What about these 27s, right? We have 2 27s there. We can go ahead and cancel those. Okay? I don't like crossing it out. You can cross it out if you want to, but it kind of makes it hard to go back and look at it. You know what? Sure, I'll cross it out. Kind of cringing while doing that, but, right, they cancel. Now, we have x to the power of 6 up top, and y to the power of 9 also up top. Okay, and do we have anything on the bottom? We don't. So we have one of 2 options. We can just get rid of the fraction, or we can write a 1 under there. Right? Because 1 can multiply anything and still equal that same thing. So it's a good placeholder. Okay. So then now equals, and we are coming back around like this. That's how the work's going. So we're going to have 6x's being multiplied and 3x's being multiplied for a grand total of 9x's being multiplied and 9y's being multiplied. Just like that. And that is our final answer. Okay. Again, you know, like I said, there's many ways to do this. And if you want, you may have seen, hey, I can get rid of this negative right here. Let me go ahead and first take care of that. You could have taken care of the negative before we even took care of the exponent. That's valid. That's okay. You didn't break any of the rules. You just applied one rule before another. That's okay. Our logic doesn't dictate that we do any one before the other. Therefore, it doesn't matter the order in which we do this. Okay? Awesome. Now on to the last one, to the beast of them all. Right? Getting a little bit of geometry in here, right? Flexing those geometry muscles. Ms. Burkhart's going to be proud of us. We're going to go into her geometry course and just crush it. She's not going to know what to do. She's going to have to find more work. It's going to be fantastic. So what is the volume of a cube with edge lengths of 6 times x to the power of 2 times y to the power of negative 1, all divided by y times x to the power of 3? So let's go ahead and first, what are they asking for? What do they want? What are they looking for? What is the volume of a cube? Okay, and so now here's where we need a little background knowledge in geometry. So a cube, drawn as best as I can. I'm okay at drawing three-dimensional figures, but definitely not the best by any means. That's not too bad. And we'll draw the dotted lines right there. That's not too shabby. It works. It gets the point across. Not perfect, but right? That's a cube. Now, how we find the cube, and this is a whole nother lesson in itself, a whole nother concept, but what you need to know about it is if we have a cube with side length a, right? It's a cube, so all of the other side lengths are a. The volume of it, v, is just going to equal a times a times a. 3 times. Repeatedly multiplying a 3 times. How do we write repeated multiplication? Right? This is basic by now. We have worked so much with repeated multiplication, we just know that's a to the power of 3. And that's what volume is, right there. Okay? So now, we need to find volume, and we just took the first step to setting this up, right? We know how to find volume, now we just need to plug in our information in the problem into this. So the edge length is this. That means that this is going to be a. Right? That's our a. Let's go ahead and plug that in. So equals 6 times x to the power of 2 times y to the power of negative 1 divided by y times x to the power of 3. And remember, all of that is getting cubed. A is getting cubed, and all of that is a. Okay? So now, here's where we're going to go ahead and make that big step. So this is for the student who is mastering. Right? The student who is mastering is going to say, I'm just going to go ahead and use my rule to multiply this to each of my exponents. Now, remember when we do this, right, the thing about this, it goes to everything that's multiplied, not just our variables, also our 6. Right? And even if it doesn't have an exponent written, like this y to the power of 1. We don't have the 1 written there, but it's implied. That also distributes to that exponent. Okay, so let's go ahead and first just write this step. It's very important to show our in-between steps so we don't get lost. And if we do get lost, we can go back and figure out where we got lost. Right, so I'm just finding these exponents by multiplying 3 by each exponent. This 6 didn't have an exponent, so that's like an exponent of 1. 3 times 1 is 3. X to the power of 2, 3 times 2 is 6. Y to the power of negative 1, 3 times negative 1 is negative 3. Y to the power of 1, right? It's not written, so it's implied that it's y. Y to the power of 1, 1 times 3 is y to the power of 3. And then x to the power of 3 times 3 is x to the power of 9. Okay, we just took care of the exponent with our new rule. Now again, you want the fundamentals of that because it's so easy to get confused, it's so easy to forget what it applies to. And the only way you're gonna remember that, the only way you're gonna keep that shortcut, that smart cut in your brain is through practice. Right? You gotta practice it. That's gonna make it permanent. That good practice makes it permanent, and then you're not gonna be messing it up, potentially. Because there's a lot of room for misconceptions in here, right? You could, we're multiplying numbers, so you could just say, oh, well, 3 times 6, right? So I'm gonna put 3 times 6, that's 18. But no, remember, they're exponents. It multiplies the exponents, not the actual number. Right? I think that's actually the biggest misconception here, or the biggest mistake I've seen made. Okay, so now let's go ahead and simplify this as much as we can. Let's get rid of the exponent on our 6. So let's calculate 6 to the power of 3. So that's just 6 times 6 times 6. And I'm cheating. I know, I'm using my calculator, but that's okay. This is what calculators are for, big numbers like this. So 6 to the power of 3 is 216. Okay? Now, so that was taken care of. Now, I have 6 x's multiplying on the top and 9 x's multiplying on the bottom. 6 of these are going to take away from 6 of these 9. So I'm going to lose 6 from my 9. That's going to leave me with 3 x's multiplied on the bottom. Also, I want to take care of this negative. I want to take care of this negative that y has an exponent of. So I'm going to do that by flipping it to the other side, right? Reversing that operation. So y to the power of 3. I'm going to consider that the first one that was already there, and now here's the one that I flip over. Again, there's technically no difference, but it's important to be clear and to know what you're doing. Okay, so 216 on top, and then we have 3 y's being multiplied and another 3 y's being multiplied. That's a total of 6 y's being multiplied, so y to the power of 6. And x is just chilling, right? It's still the same as it was before. X to the power of 3 goes right there. And that is the volume of our cube. Right? And it looks weird. It's variables. But understand, that's just because we don't know what x and y are. Right? I could give you x and y. Say that I gave you a 2 for x and a 3 for y. You could then actually find out the number for that volume, the actual quantitative amount. Alright? But understand, variables, they're actually quite a blessing. They're a very useful tool. So when we get answers with variables, when we work with them, don't let them scare you. Alright?